I know, big, yeah, that would be the one thing. Now we're recording. Check. Welcome. Yeah, otherwise today would be the day that I would forget to record. All right, so a couple of things. And this is totally my bad. The quizzes, I'm not used to having quizzes, so I've really let those slip. So what I've decided to do, because we don't really have time to use class time, what I've decided to do is just give you longer, like a longer time period. It's still going to be a 20-minute quiz. So I posted quiz 4. So quiz 4 is available. Quiz number 4 is on, and I have it here, 5.1 to 5.3 and 5.6, I guess, to 5.7 and 5.7. Okay, this is meant to be an easy quiz, okay? Because this was a while ago, right? So this is just making sure that we're on top of kind of quick chapter 5 questions. Okay, so this is meant to be easy, to be an easy quiz. Okay, so of course I don't want you to kind of head into it blind, but just keep that in mind. So they're going to be short answer questions, kind of short answer style, just making sure that you know some of those basic calculations, okay? So it's going to be available until I decided Thursday at midnight. Thursday at, everyone hates it when I do 24-hour time, 23:59 or 11:59 p.m. And it's a 20-minute quiz. 20-minute quiz, but no class time will be given, and I am sorry about that, but I would prefer to just use up that 20 minutes to go through more examples of chapter 6 things. So so that's what I've decided, and I think what we'll do going forward is I'll just make the amount of time that these quizzes are available for longer, like I did today, and then we won't be using class time. Because I am feeling the pressure a little bit. You guys are probably not. That's okay. That's not for you to worry about. That's for me to worry about. So no class time will be given. Sorry. Okay, just got a message. So you guys are no strangers to those where the teacher just wants to have the class time to, I want the class time for me. Okay, so okay, so that's good. What were we doing? I had got notes everywhere. So I will be posting a quiz number 5 as well, and it's going to be on the beginning part, but you'll have until probably Tuesday next week. So quiz number 5, because what I realized was as it stood, I think we'd obviously only done 3 quizzes. So for a total of 25%, those are pretty heavyweight quizzes. I don't want that. I want these quizzes to be kind of manageable, bite-sized. And so, so I will be hitting you with quizzes, but we also have test 3 coming up. And I know we just wrote test 2 and it feels like, but that's just kind of the end of the semester. So quiz number 5 will be open until Tuesday, April 6th. All right. Okay. At 11:59 p.m. again. Okay, so I'll post quiz number 5, and it's going to be on stuff up until what we've covered today. Then, so it'll be open for a week. But again, it's just going to be a 20-minute timed quiz, unlike the assignments where you have time to sit down and work through some stuff. Okie dokie. So I posted a lot of documents on Moodle. I posted Chapter 6 examples, Chapter 7 examples. I also posted the Chapter 6, Chapter 7, and Chapter 8 problems from the textbook, like I was doing before the tests, but now I'm finally working ahead, I guess. So have a look at those documents that I posted. See what's up. So for some quick review, we talked about all these different ways that we can manipulate interest rates. So 6.1, I don't know what it's actually called, probably the basics. He likes to do that. Effective and equivalent interest rates. It's like the first time the first section isn't called the basics. Okay, so I'm going to call this effective and equivalent interest rates. Okay, so what we decided, that would be rude, wouldn't it? If we have a quiz and a test. I have test 3 on the 8th. Let me check here. It's gonna make me sign in here. Okay, phew. But of course, so that quiz that's due on the Tuesday will help you prepare for the test. So it's not all bad. Okay, yeah, April 8th. And I guess we know our final exam. Right now, I can't remember. I can look it up. It is on the 26th, which I should update there. But okay, April 8th. So yeah, the 114 final exams are always, I must have flip-flopped between the 6th and the 8th. It's the 8th. I'm committing to the 8th. 22nd. No, thank you. Yeah, 114 is always at night because there are night sections. I guess there's a rule that if there are night sections available, the exam has to be at night. I know. Better caffeinate. So we need to be able to manipulate interest rates. Okay, and we sort of introduced the idea last day where if we have these regularly scheduled payments, right, then we're going to have some payment frequency which isn't necessarily the same as the compounding frequency. But to get around that, we adjust our compounding frequency to match our payment frequency. And I will say that again, I'm not going to put that in the review here, but I will say that again when it comes up. So, but just in general, we need to be able to manipulate interest rates. So we introduced moving from one frequency to another. moving from one compounding frequency which we'll call F subscript 1, okay, so the first compounding frequency, to another compounding frequency, which we'll call F subscript 2. So then we had, oh, not in our examples, our formula sheet. Where is that darn thing? Here. So we talked about all of these, but from our formula sheet, the one that's the most important that I need you to have handy at all times is this one, right? I2. So here we're moving from a frequency F1 to another frequency F2. Okay, this is going to be the most important formula of all of these. Most important formula of all these. Okay, the other ones are special cases. Notice that we have some effective rate, right? So here we have 2 effective rates. The effective rates are the special case where, okay, what is the equivalent annually compounded rate? Okay, so it's kind of a weird special case that I don't really care about in general, but it's introduced here, so we should probably talk about it. The effective rate, which we denote by I subscript EFF, okay, is the equivalent annually compounded rate, okay, is the equivalent annually compounded rate. Essentially letting F2 be 1, right? Because we're moving from some frequency F1 to another compounding frequency F2, but for the effective rate, we're basically letting F2 be 1. Right, so let F2 be 1. Okay. We have 2 formulas for these effective rates, as well as for I2 and R, and these were special cases where if we have continuously compounded something or other. I know, not very clear. But what I want to do is, from the Chapter 6 examples, I've got quite a few examples from 6.1, even though we did it last day and we're just reviewing. So what I want to do, instead of actually calculating these, I just want to talk about what is each question asking us to do, right? And also write down which formula should we be using here. So the first one, I guess I'll call this the end of our review. It's not really, but we haven't done these examples before, so I can call it here. So an investment earns 5% interest per year, compounded semi-annually, right? So our compounding frequency F1 is 2. How much interest should alternative investments, which are compounded quarterly, pay? So here, F2 is 4. And what you can think about is, because we're going to be using our calculator functions, remember our calculator had the notation compoundings per year and the payments per year? Right. So I'm just using that notation from our calculator because then it'll be easier to make the connections, right? So the compoundings per year is my F1, which is equal to 2. My payments per year will always be, oh, now I've done it, haven't I? I skipped ahead too much. Sorry. Delete that. This will be the payment frequency. Sorry, I skipped ahead. I don't know why I did that. That's okay. Back to where we were. So F1 is 2 and F2 is 4. I1 is R over F1. Okay. So this is the only one that we're going to do because it's the only one I want us to practice. 0.05 divided by 2. 0.05 divided by 2 is 0.025. So then, how much interest should alternative investments, which are compounded quarterly, pay? So I'm going to find I2. Probably the question is asking for R, but I'm not going to take it that far. So I2 from our formula sheet, remember, this is our most important one, right? I want to go from compounding semi-annually to compounding quarterly, okay? Which means I need my I1, but that's just the I that you're used to finding. So 1 plus I1, it's 1 plus I1 to the power of F1 over F2 and then minus 1. So I2 is 1 plus 0.025 to the power of 2 divided by 4 minus 1. Make sure you subtract that 1 at the very end, right? You don't want to incorporate that minus 1 anywhere else. So let's do this on our calculator. Let's see if it behaves here. First thing I'm going to do is I'm going to just confirm that my 0.05 divided by 2 is in fact 0.025. But then from here, what I can do, because I'm working inside those brackets, and it's hard to see here, but I can add 1. Okay. And then I want to take that to the power of 2 over 4. So then y to the power of x, and then to make sure that that 2 over 4 stays inside all in the power, I'm going to use brackets. Bracket 2 divided by 4, end bracket. Careful, because it'll show you what 2 divided by 4 is when you hit the end bracket. That's not actually what you want. You want to hit equals, and then that's the answer that you want, and then minus 1 to make it a periodic interest rate. So this is the periodic interest rate compounded quarterly. Let's see if I can remember any of this. 0.012422. I lost it. Why would it recommend that to me? Sometimes I'm like, the game looks pretty good. Most of the time I'm like, why would you try to push this on me? Oh, and I wonder if I can, oh, it doesn't do that. Okay. I'll just do it quickly on the side here. 0.025 to the power of 2 over 4 minus 1. All right, here we go. So I get 0.0124228367. Okay. So this is the equivalent periodic interest rate compounding quarterly. So, good. For the other examples here, I just want to go through and read it. Okay. So what is the effective rate? Okay. So here we want to find the effective rate. So EFF, effective rate of an investment which earns 3% compounded biweekly. So here, right, we're moving from biweekly, and then what's implied with the effective rate is we're moving to compounding annually, right? And so because we're compounding biweekly, we would use this formula here, right? This formula for the effective rate is for compounding continuously. So what I'm going to do is I'm going to show these here. So these are our two options. Two options for the effective interest rate, right? Because at this point, the formula sheet has been overwhelming the whole time, right? But especially when you flip it to the back page, right, the second page, it just is really overwhelming, right? So I just want you to practice just kind of figuring out what each thing is and what can you ignore for each question. So here, if you're finding the effective rate, only one of these is going to work, right? And so what we need to know is that this, whenever you have E, this is for continuously compounded. But we don't have that, right? So not this one. We're going to be doing this one, where I is 0.03 divided by 26, and F is 26. Okay. So like I said, we're not going to do the calculation. You can easily do the calculations, but okay. So the effective interest rate, remember, is just going to compounding annually. And you actually could, as long as you remember that definition, you actually could use that I2 formula that we started with F2 being 1. Here, an investment earns 6% continuously compounded interest. Now, what's the effective rate of interest? So now, of course, I have continuously compounded interest. So then now, let's see here, copy. Now, I can't use this one, right? I can use this one for continuously compounded. With R is 0.06. Notice that that's the only thing that you need, right? And that's the only thing you get for continuously compounding. There is no frequency, right? And so here, R is 0.06, and that would be, once you do the calculation, that would be the equivalent annually compounded rate, because that's the definition of the effective interest rate. Okay. So let's see here, put it on a new page. An investment earns 5% interest per year compounded quarterly. Yes, so by definition, the effective interest rate is annually compounded, which I hope I jotted down here. Yeah. So the effective interest rate is always just moving to annually compounded. So it's just a special case of annually compounding. Awesome. Good. So an investment earns 5% interest per year compounded quarterly. what is the equivalent continuously compounded rate? So now you want to move from some compounding frequency, right? So move from F is 4 to continuously. So we want to find the rate, the continuously compounded rate, which is denoted by R. So looking at the formula sheet, I'm going to mark it up so I can bring it up to the top here. Oops. If we have a look at these, right, just kind of elimination strategy here. Well, I don't want the effective rate, so neither of those are going to work. And it has to be continuously compounded, right? And so this region here is my continuously compounded region, right? Everything having to do with continuous compounding happens over here. So unless you have that special case of continuous compounding or want that special case in this case, that's when you move to this portion of the formula sheet, but otherwise, no, you can just leave it alone. So here, this formula, just looking at it, well, this is moving from some continuously compounded rate to some compounding frequency F2. But what we want to do is we want to move from some compounding frequency to moving continuously. So what we want is this guy here, right? Because we want to find, so the rate that we're moving from, or the frequency that we're moving from, will always be F1. So F1 is 4, and then you can think of the continuously as your F2, but it'll just be continuously, so it doesn't exist. So here you have F1, and you want to find the rate. Here you have some desired frequency F2, and you want to move from continuously. Okay. So here we're going to be, R is F1 times the natural log of 1 plus I1, where, we're trying to find R, where F1 is 4 and I1 is 0.05 divided by 4, just like before. Okay. And then that last example, course, just highlights the last formula here. What monthly compounded rate is equivalent to 9.5% compounded continuously? So now you want to move from continuously to a new frequency. So here you want to move from continuously to F2 being monthly 12. Or maybe I'll just write F for now. F equals 12. So we already discussed it up here. So that's going to be this formula, right? Because continuously compounding is involved, I know I can kind of zero in on this region here of the formula sheet. Okay. So it's not this one because we're not moving to F equals 1. Okay. And it's not this one because we want the new compounding frequency to be 12, right? Not moving to continuous compoundings. Using all kinds of abbreviations at the edge of the page here. Okay. So what that means is the only one that we have left here is I2. But notice, right, that the continuously compounded rate, so where R is 0.095 and F2 is 12. So what I want you to remember is F1 is always the frequency that you're starting at, and F2 is always the frequency that you're ending at. Okay. So here, just a note, F1 is always the frequency, because I know we're gonna probably have some trouble with F1 versus F2 later. So I just want to really hammer it home. So F1 is always the frequency that we start at. And F2 is always the frequency we end at. Okay. Good. Okay. So, all right. You ready to talk some annuities? We sort of talked about them last day, but here we go. So 6.2 is on annuities. Yeah. So what is an annuity? An annuity is as soon as you're making regularly scheduled payments. Okay, so giving you some payment frequency. So an annuity is when we make or get, right? There could be instances where you make an investment and then in return you get, $300 a month or whatever. So RRSPs being one of those kind of most common. We talked about set for life, right? You get $1,000 a week or a day or something for 25 years. Right, so those are all annuities because they've got these regularly scheduled payments. What we're more used to seeing is probably things like car payments and mortgage payments where we have these regular payments. So an annuity is when we have regularly scheduled payments. Okay. At some payment frequency. So I'll just say that at some payment frequency. Okay. So we need some way to talk about or to calculate the future value of an annuity, right? So if I invest $100 a month for 25 years, right? What is my future value, right? Each $100 is going to be earning different amounts of interest. So you can imagine $100 a month for 25 years. Can you imagine your timeline? You'd have to calculate a ton of different future values and then add them all up, right? And so that sounds terrible. So just imagine find the future value of, I'm just kind of winging it here, so sorry, of deposits worth $100 each month for 25 years. maybe even after, can we get crazy? After 30 years, right? Something like that. I'm not giving more information, but imagine having to solve this only using the compound interest formulas that we have, right? So here, we need more advanced formulas than just the future value is the present value times 1 plus I to the power of n, because you'd have to do this for each monthly payment, right, for 25 years, and then it sits there for 30 years, right? So the payments are only happening for 25 years, but then they sit there making interest for 5 years, right? And so it just makes a real mess. So we would need more advanced formulas than this, because this would require us to do, we would need to find the future value for each $100 monthly payment and that's a no for me. No thanks. Imagine your timeline. Ugh. 1 month, 2 months, 12 ticks per year, 12 times 25, and then a little bit longer for 30 years. No. So that's why the formula sheet is a little bit nasty on the other page, right? And so what I want to do is just look at the formula sheet, okay? And let's just focus on, so the left-hand side of your formula sheet, like I said here, is from chapter 6. And then when we move into chapter 7, which will be quite soon, because they are, you can see that they're very similar. If you do a little compare and contrast, the main difference is that you have these little subscript due, okay? And then it tacks on a little bit of interest. But besides that, there's nothing really going on, changing between chapter 6 to chapter 7. It's just we need to identify which situations do we use the left-hand side and which situations do we use the right-hand side. Right. For now, we're just sticking to the left-hand side. So what I want to do is I want to focus on the future value and the present value formulas. Okay. So from your formula sheet, okay, notice that you can either find the future value or you can find the present value. So they're not linked up anymore. The idea being, well, we can't link them because the future value would be after, okay, so I make some payments, and how much do I have in the end? Right? How much have I saved? If I put away $100 a month for 25 years, how much have I saved? Assuming I didn't start with anything, right? So then the present value would be 0. If I'm talking about a present value and I'm solving for a present value, then most likely what's happening is these payments are to pay off some loan, right? And so notice, notice that we need to decide if we're solving for the future value or the present value before we do any calculations. If we are solving for the future value or the present value, before we can do any calculations. So just an example, so the future value, if you're finding the future value, you would be finding things like, so most commonly, there are of course other examples, but most commonly the future value is you've put away savings, how much do you have in the end, right? So investing and how much do you have saved? I'll scoot this over so I can keep this. Do you have saved? Okay. Notice that if you're making investments, right, typically we start with nothing, so the present value would be 0 in that case, right? And so that's why there is no PV in the future value formula, because, well, we would start at 0, so we can ignore it, right? An example of, or a very common example of when you would need to find the present value is if you've borrowed some money. So the present value is some loan amount being paid off. Same idea. If at the very end of this, right, if the loan is paid off, then the future value would be 0. So then the present value doesn't care because the future value should be 0. So if the loan is paid off, the future value would be 0, right? So I borrow, let's say $10,000, and then I'm making weekly payments of $200 maybe, right? So I'm chipping away, so each $200 that I pay chips away at that present value, and then at the end of that term, right, however long it takes me to pay that off, the future value should be 0. Okay, so those are just things to keep in mind, and that's why in the future value formula, there is no present value, and in the present value formula, there is no future value because it should be 0. Okay. Okay, so let's talk about our timelines for this. So what happens, I feel like we've already talked about the PMT, that's why I keep skimming over it, but let's just introduce what each of these variables are. So of course we know the future value and the present value. I'm assuming that we're okay with those. The new ones are the PMT and I and N, which have morphed a little bit. They're exactly what you're used to seeing, except now I is going to be the periodic interest rate compounding at the payment frequency, and N is the number of payments. Okay. So I'm just going to copy this here again because I don't want to be scrolling around. So here, where the PMT is going to be the regular payment amount. So when I say regular, I mean regularly scheduled payment. So what I'll say is that it's the payment amount. So if I'm paying $100 a month, then the PMT would be 100. And that goes for both of these, right? The I in each of these situations are going to be I2. Okay, so I is I2. Not for me. I always find it easier if you just force yourself to just always calculate I2, then it's not something that you have to think about later. Okay. We will find that we don't need to find I2 every time. And that is if the payment frequency and the compounding frequency are the same, right? But I'll show you an example, and there's really no harm in finding I2 every time. So I2, which is 1 plus I1 to the power of F1 over F2 minus 1. And we talked about those last day and established what all those variables are. And then N is the payment, number of payments. Number of payments. Oh, sorry, I feel like I've got like a calcification here inside. Something's going on. So I'm having a hard time writing, and it's really annoying. But something's bound to break down before the end of term, I guess. But it's the number of payments that we're making. Okay, and so that's going to be really important, because remember, N was the number of compoundings before. So now we have to change gears. And as soon as we see those regularly scheduled payments, you know, $100 a month, $10,000 a year, that kind of thing, then we need to think, okay, my N is actually my number of payments now. And we talked about that last day, right? It's because the bank can't call you up and say, hey, we really need you to be making weekly payments instead of monthly. That's okay, right? That would be weird. They can't do that. I'm sure they tried at some point, but it doesn't work that way. So, so then they need to make adjustments, and that's what we're doing in our math. So now let's talk about our timeline. So for annuities, right, we've got these regularly scheduled payments, right? What I want to see are the first 3 ticks and the last 2 ticks. Okay? So at least. So for annuity timelines, you must show at least, and I tend to do the bare minimum here, you must show at least the first 3 ticks and the last 2 ticks. So what that's going to look like is if you have kind of, maybe you're starting today, you know, what we can do is if we were to map out that example, so you're making $100 payments per month starting today for 25 years. Okay. And then we wanted to know how much do we have after 30 years. Okay. I didn't give an interest rate or anything like that. This was just an example that we came up with on the fly. But what I want, so this part is an annuity, right? So here, where I'm making regularly scheduled payments, this is the annuity. So the timeline for this portion would be, okay, here I am at 1 month, 2 months, okay? That's the first 3 ticks, right? Today is a tick, 1 month, 2 months. And then 25 years has how many months? 25 times 12 is 300 months, which I'll put kind of on there as well. It's nice to have the 25 years because that's referring to the fake question that we're talking about, right? But then I want the last 2 ticks, so backtracking it to 299 months. In between here, you can fill it with a dot, dot, dot. Right? We can just say it keeps going like that, you get the gist, right? 1 month, 2 months, everyone would pick up on, okay, monthly, great. Okay, so then what you do is you put your payment amounts, 100, 100, 100, 100. By default, the payments are made at the end of each month, right? So if I'm starting today, then at the 1 month mark, just before that 1 month starts, I would make a payment right at the end of today's month, I guess. So that's what these are going to look like. So now what you can do is you can just funnel these, right? In theory, each of these has a little future value arrow. We'll be able to find the future value either at the 25-year mark or if we calculate it as an annuity, which I would prefer to do because yuck, we can funnel these and use the future value calculation for an annuity, right? And then we can take that future value to be some other future value 5 years later. So here, what you do is you show that this becomes some future value 1, where n is the number of payments, which in this case is there were 300 payments. I did make this question a little bit more advanced than what we're going to be starting with. But of course, I just wanted you to see what happens here. So here, you can connect with 3 dots just to show that, hey, it just keeps going. And here, I just kind of think of it as funneling. So you can funnel all these payments to one future value. Funnel the payments to one future value. Oops. Okay. So however you want to show, if you don't like curved brackets or curly brackets, you can use a square bracket, right? But I just want you to show that you're gathering all these up and using that future value formula that we just introduced, right? I can find that future value that takes into account that I'm taking $100 a month or I'm depositing $100 per month for 25 years. So then if we actually had to answer this question, right? So now I stopped making payments for 5 years, but this amount would still be sitting here earning interest, right, for 5 years. So now, because there are no payments, this is just a compound interest problem, so a Chapter 5 problem, right? So here, this is just a compound interest which is from Chapter 5, right? Because you're just taking some amount and it's sitting there for 5 years. So what this becomes is this future value 1 becomes some future value 2 after 5 years. Okay. So we're going to be connecting our annuities with our compound interest. Notice that annuities they will always have compound interest, but when I say compound interest, I'm referring to Chapter 5, right, which is what we were just working on a lot. So this, of course, was a bigger question than we actually are going to solve for now, but it is something that you will be able to solve eventually. Maybe even this week. Can you imagine? Okay, so let's do a reasonable example. Martha contributes $10,000 each year to her RRSP. A rate of interest of 7% per year. How much will she have after 25 years? Now, the first thing, as soon as you see that, okay, she's making regular payments, right? $10,000 each year, right? So every year she's making payments of $10,000. I need you to figure out what the payment frequency is. So it looks like it's yearly, right? And also check what the compounding frequency is, okay? And so kind of first stop for these problems is going to be to figure out what the compoundings per year are and what the payments per year are. So the compounding, or sorry, yeah, the compoundings per year seem to be just 7% per year. So the compoundings per year is going to be 1, right? But this is also my F1, which is 1. This F1 and F2 situation, that's just worth memorizing, or in your case, just having available on some sort of, maybe even on your formula sheet, right? And so here, this is just memorize this until it starts making sense when you think, okay, I'm moving from the compounding frequency to the payment frequency, right? So here, just memorize for now. And it will make your life a lot easier. So the payments per year are what each year? So she's making annual payments as well. So it's 1. Okay. The payment amount we're told is $10,000. So I'm going to jot that down, $10,000. And 7% is the rate. So R is 0.07. And T is 25 years. Okay. So we have a lot of information. None of it really looks like something we can work with yet. Okay. But like I said, your first step is to check, do I have the same compounding frequency as the payment frequency? If you do, you do not need to find I2. But like I said, it doesn't hurt to always just get in the habit of just finding I2, because if you don't and you need it, it just is completely wrong, right? And so here, since F1 equals F2, which equals 1, we don't need to find I2, right? But there's no harm in doing it. We do not need to find I2, but there is no harm. There is no harm in always doing it. Just in case. I'll even put a little exclamation mark there. Okay. So what we're going to do is let's find I2, and remember that that's the I that we're going to use in our calculations. So I2 is 1 plus I1 to the power of F1 over F2 minus 1. Remembering that I1 is R over F1. And often I'll just throw in my calculation for I1 inside here. If you don't like doing that, that's fine. You don't have to. You can do it on the outside and then plug it in. But what it looks like is I2 is going to be 1 plus 0.07 divided by 1, going from F1, which is 1, to F2, which is 1, and then minus 1. You'll see that nothing actually happens here. And so that's why there's no harm in doing it. So if you just get in the habit of doing it, eventually when you see that, oh, these are the same, so I don't need to find I2, that's better than trying to figure out, do I need to find I2? Right? It's a better direction to move in. So when you realize that, oh, I can just skip that calculation because I don't need it. So I2 is 1 plus 0.07 to the power of 1 minus 1. I don't really need a calculator, right? Because 1 plus 0.07 to the power of 1, so I2 is 1.07 minus 1. So I2 is back to 0.07. So notice that it hasn't changed. Notice I2 equals I1, which is 0.07, since the frequencies are the same. Okay. So this is the I that we use in our calculations. I2 equals 0.07 is the I we use in our calculations. Okay. So now let's figure out, and it might be easier if we just map it out with a timeline, but usually I'll find I2 before I even go sit down to do the timeline, just because I know I'll need it and it can be annoying and I just want to get it out of the way. But so now let's draw the timeline. We could have drawn the timeline first. In fact, I'm going to bring this down so that I can read it while I do it. I'll delete it in a bit here, so that's why I'll kind of get up to the top. Okay. So Martha contributes $10,000 each year to her RRSP. So at some point, let's just call it today, she decided that she was going to do that, and she's going to do it for 25 years. So here we are 25 years later. And so she's going to make 25 contributions of $10,000, right? Because for 25 years, she's making yearly contributions. So here we are at 1 year, 2 years. And then remember, I want to see the first 3 ticks, 1, 2, 3. And then I want to see at least the last 2 ticks. So 24 years, and then let's jot down 25 years, and then let's jot down 24 years. And then I do want to see the ... Otherwise, it doesn't really make sense, because if you just left it blank here, then you're really saying that nothing happened, right? Whereas the ... says, okay, you get the idea, just keep going. So how we're doing these problems is the payments are being made at the end of each year. And then the only thing that changes in Chapter 7 is it would be at the beginning of each year, which would shift this payment to today, and it would shift all the payments kind of back a tick, and that's all we're dealing with in Chapter 7. So we got $10,000 here, $10,000 here, and then our last $10,000 here. Okay. So how much will she have after 25 years? So that means that we have to find a future value, and to show that, remember you can use a square bracket if you want. I like drawing curly brackets. So, and then that future value, our calculations can only go until the end of the payment, so the last payment. So this here, again, we're moving forward, so this is going to be a future value. On the arrow, you're going to have the number of payments, right? In this case, it's yearly. It's a nice and easy problem, right? So n equals t times f2, because f2 is the payment frequency. So now 25 times 1 is 25, which makes sense, right? We're making 25 payments of $10,000. And what's nice is we've already found I2 up above, right? So here somewhere I can write down that I2 is 0.07, right, from above, from calculations above. So that's what's nice about finding I2 before you do your timeline, is it makes your timeline look nice and neat. Okay, so now we're gonna grab our future value calculation, right? And so each of these guys here are PMT amounts. So you make a payment here, a payment here, a payment here, a payment here, and we want to find our future value. I'm just going to grab it from the formula sheet. Oops. Notice that there's no mention of her having any money in the account, right? She just started blank slate, $10,000 each year for 25 years. How much is she going to have? So the present value would be 0. So the formula that we need, of course, is the future value formula. So here we are, right? And I'm going to plug in my values here. The payment amount is 10,000. Big square brackets means that we have to simplify inside those brackets before you can multiply by the PMT. And I just realized that I didn't give you guys a break, but how about this? I promised to end early instead. How about that? I know, we're on a roll here. Okay, so I know ending early, it's always nice. So let's see here. My I is going to be 0.07, right? And remember, my N is 25. So I've got 1 plus 0.07 to the power of 25, and then minus 1 over I again, which is 0.07. Later on, you're going to have quite tricky values for I, right? Remember, we've seen I's that you have to store in your calculator. Same goes for these ones, right? So once you've calculated your I2, you might want to store it, even if it's nice and simple like this one. So it's important that you do these calculations in the right order. All right, so first you have to add 1 and 0.07. Then you have to raise that to the power of 25. Then you subtract 1. Then you divide by 0.07. Then you multiply by 10,000. Right? So how can I show that here? So here, step 1, and then 2, and then 3, and then 4. So that's going to be really important. And then you can multiply by the 10,000. I don't typically end up showing the work because it's actually more annoying to show the work here. So I will for this problem, but typically I would just calculate this as one value. I would write that down times 10,000. So for now, I'm going to show all these steps, but typically I would just skip to the second to last step. So the future value is 10,000 times 1.07 to the power of 25 minus 1 over 0.07, which is going to be 10,000 times, and then I'm going to do it on the side here, but just make sure you get the same value as I do. 1.07 to the power of 25 should put you at 5.42743264. Presumably it keeps going, but we ran out of display space, right? And so you want to keep, you don't want to clear that, you want to keep that in your calculator. And then minus 1 over 0.07. Next step, so just keep that on your screen, the 5.4, blah, 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 and then just subtract 1, minus 1, putting me at, and it seems silly, but you do have to keep writing all the outside stuff that isn't changing, right? You can leave the future value. I don't typically write it unless something's changing, but I shouldn't do that. It's okay, but I'm trying to teach you proper math rules. 4.42743264, and of course if you are tempted to clear your screen, you don't actually have to, because the next step is dividing that by 0.07, right? So as long as you're not clearing your screen and trying to re-enter those, it's okay, you don't have to store them, but it might be easier for you if you have a hard time. So now the next step is dividing that by 0.07. So the future value is 10,000 times 63.24903,772. So usually I would just skip from here to here, right? Making sure that you keep all your decimal places. So here, typically, I would skip to here. Make sure you keep all your decimal places. Make sure you keep all decimal places, right? Even the ones that aren't shown. So I do like to show that 63.249-ish times 10,000, just to kind of get back in the groove. On our test, do we have to write that? Or, yeah, so here, you do not need to show, you need to show plugging all the values in, because I need to see that you know which values go where. But then if you just skip straight to here, that's totally fine. In fact, I encourage it, because it would just waste your time trying to write this out when the calculation is so kind of quick on your calculator after some practice. So don't worry about writing those steps out. you two can just skip straight ahead. So then I can multiply by 10,000, counting my zeros here at 10,000. I get a future value. And just like before, I'm going to write out all my decimal places and then do my rounding just in case I muck it up. 632490.3772. So then I can round to 2 decimal places because this is money, of course. So 632490 and 38 pennies. Okay. Let's take it a little further, right? So this is how much she's going to have at the end of 25 years, right? How much has she actually invested, right? So here versus Martha invested, she invested $10,000, right? So to her, only $10,000 or only $10,000 each year are going out, right? So she invested 10,000 times 25, which is hopefully, let's see here. Okay. Zeros were failing me. I was reading this as 63,000. It's not, so it still makes sense. Okay, good. I was worried I had screwed something up. So she invested 250,000. So, okay, so we're back on track. Okay. So how much did she make in interest? Right, to her, out of pocket, she's only missing $250,000, right? But in return, at the end of these 25 years, she's going to have $632,000. That's where my eyes deceived me. I had dropped the zero. Didn't make sense. So therefore, she made, or she will make, I guess. She will make $632,490.38 minus $250,000, which is what? $632,490.38 minus $250,000. Okay, checks out. $382,490.38 in interest. That's pretty good. She also had a huge interest rate helping her out, but that's the idea, right? So the time value of money is going to be really important, especially if you're making multiple payments, right? Each of those payments are going to be accruing interest as you go along, right? However, the $10,000 invested at the 24-year mark is only sitting there for a year versus the $10,000 that was invested at the 1-year mark, right, has been sitting there for 24 years earning interest. And so the calculation that we just did takes that into account. So pretty cool. Good. Okay. Let's do another example. I just think some of these examples I just picked because the question is funny. Hank borrowed money from Tank. Hank agreed to make yearly payments of $2,500 for 12 years. If Tank, okay, so Hank is borrowing money from Tank. I don't know, I think it's funny. If Tank charges interest of 13% compounded annually, what was the amount of the loan? right? So as soon as you want to find the amount of the loan or how much did they borrow or whatever, this is find the present value. Because the present value, so you've got some initial loan amount, and then we're going to try to pay it off with these payments, right? And so this is going to be a typical setup for when you have to find the present value. So notice we just found the future value, and then we're going to find the present value, and then we're going to work through the formulas just like that. Okay, so let's map this out first. So I know I'm mixing things up. Keep you on your toes. Nah. I said I wanted you to write out your compoundings per year and your payment frequencies. All right, let's start there. Only because it'll help us out later. So the compoundings per year and the payments per year, we need to figure out, well, compoundings per year is F1 and payments per year is F2. All right, I'm going to end up just following the same procedure, and maybe that's a good thing that I did earlier. So he's making yearly payments. So the payment frequency is yearly, so once per year. And Tank charges 13% compounded annually. So then F1 is also 1. So then, right from before, we know that I2 equals I1, which is R over F1. Okay. You can go ahead and just calculate I2 right away, right? I2 is 1 plus I1 to the power of F1 over F2 minus 1. Notice that what we get is 1 plus 0.13 divided by 1 to the power of 1 over 1 minus 1. 0.13, 13%. Okay. So there's no harm in going through and finding I2. In fact, I encourage it. Yeah. So now let's map this out. Let's use a timeline to map this out. So, and I'm going to bump this up just one line because then I can have the timeline on same page here. Okay, so we'll start today. Hank borrowed money from Tank. We'll just assume it started today. And he's making yearly payments for 12 years. Okay, so the length here, the term is 12 years. And he's going to make yearly payments. So remember, I want to see at least the first 3 ticks and the last 2 ticks. Okay, with a dot, dot, dot in between. So 1 year, 2 years, dot, dot, dot. 11 years, 12 years. Maybe this should look more like 11. Okay. So now the payment amount, right? So here, this is my payment amount. PMT is 2,500. And that's meant to pay off the total value of the loan. So here I've got 2,500, 2,500, dot, 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 2,500, 2,500. So if I want the value of the loan today, right, I need to pull all these amounts to today, right? Because all of these 2,500s are paying off some total value today. So here, what we get, again, I'm going to funnel these, zip them all up, and I can find some present value, and that's the total loan amount. Total loan amount today. only thing missing is our N, right? And so N, we still put on our arrow here. N is the time times F2, right? The payment frequency, because N is the number of payments. So we get 12 years times yearly payments, just puts me at 12. Okay. And then I just found it up top here. I2 is 0.13, but let's just say I2 is 0.13, somewhere down here, just to kind of have a nice looking timeline. Okay, so now let's grab our formula sheet. I want to find the present value. It looks very similar to the future value formula, right? Similar but not the same, because you start with your payment amount, okay, fine. But then you do 1 minus. You still have 1 plus I, but notice that it's to the power of negative n, and then over I. Right, so again, I'm going to plug in all the information that I have, and we get the present value is 2,500 times 1 minus 1 plus 0.13 to the negative 12 over 0.13. What if you accidentally use the future value formula? Then what you would be saying is that you're saving 2,500 every year for 12 years. How much do you have at the end of that 12 years, right? Which is not what we want to find here. Okay, so again, order of operations is going to be really important. So you want to do 1 plus 0.13 to the power of negative 12, and then 1 minus that, and then divide by 0.13. Okay, so again, I'm just going to do these steps just once, and then I'm not going to show the steps again, right? So we have 2,500, present value is 2,500 times 1 minus 0.13 to the negative 12 over 0.13. Next step, 1.13 to the negative 12, 1.13 to the power of negative 12. Make sure you put that negative 12 in brackets just in case, right? You don't want to have it to the power of negative and then 12 just kind of hanging around. So you get 1 minus 0.2307058878. Here, I'll make a note that I'm going to store this in 1. Just to emphasize that you need to keep all those decimal places. And then what you want to do is you want to go 1 minus store 1. Okay, so 1 minus, or if you're getting more comfortable with your calculator, right, you can use that previous answer button, which is the second menu above the equal sign. So the present value is 2,500 times 0.7692941122 divided by 0.13. So divide that by 0.13 and I get 2,500 times 5.917647017. Okay, and I'll just make a note here. Can skip from here to here. Okay, but I just wanted to show you the order of the math, right? That's just to show you kind of the proper order of doing it. Okay, so now if we multiply this by one plus I, okay. Oh, okay, yeah. So now times 2,500. So the present value, and again, just to make sure, I'm just going to write out all the decimal places, 14794.11754 puts me at $14,794.12. So this is how much Hank borrowed. Hank borrowed money from Tank. This is how much they borrowed versus how much did they pay? Paid 12 times 2,500, 30,000. So it cost them 30,000 to borrow $14,794.12. Oh, okay. So you want to make sure the main thing that's different here is that your power of -12, you probably want to wrap those up in brackets, the -12. So I'll go to my calculator here and I'll go through it. Maybe later. Okay, so I do 1 plus 0.13 equals, and then I want that to the power of -12. So y to the x button, and then bracket, and then I think this calculator 12 negative, so there's a plus minus, and then end bracket equals. Why does that look different? I'll keep going, but I can't remember what I said. 0.23. 1 minus that guy. Okay. And then divided by 0.13. 91764. Okay, no, that's the same. All right. So you want to do 1 plus 0.13, then to the power of -12. And to get that negative, you hit that plus minus button right by the equal sign. So to the power of 12 negative. Okay, it seems to work without the brackets. I like brackets just in case. Then I want to do 1 minus this. So whether you want to store it or use the previous answer option, 1 minus, I like the previous answer button. So second equals answer equals. If you don't hit equals, it's not actually going to do it. And then divide by 0.13. Cool. And then times 2,500. Good. Good, 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 good. Whee. Okay. So how much did he pay in interest? Well, he paid 30,000 minus 14,794. So interest paid must be 30,000 minus 14,794 and 12 pennies. 14,794.12. A nasty 15,205. $1.88. Ugh. No, thank you. Okay, let's see here. We have it in us to go, because I don't want to do 6.3 because that's calculating the PMT and finding N. How long is it going to take? But I do want to go straight to 6.4 because we can do it. We can handle it. And it won't be that bad. Because now, so now we're making month-end payments. So monthly payments on a car for 4 years. If the rate of interest is 5% per year compounded quarterly, yes, first time that they're not the same, and that's why I wanted to skip ahead, because most of the time they're not going to be the same. So I just want to show you that there's really nothing you can't handle at this point. So my compoundings per year is my F1, which is 4. And my payments per year are monthly, so F2 is 12. Whee! Not the same. So we need to find I2. Because what happens is, we've talked about this quite a bit now, I can't change my payment frequency. I can change my compounding frequency to match the payment frequency, right? And so what we're going to do is we're going to morph from compounding quarterly to compounding monthly. So then I2 is 1 plus I1 to the power of F1 over F2 minus 1. So I have 1 plus, and I'm going to do my I1 calculation in here, kind of easier, 0.05 divided by 4. And going from quarterly to monthly, and then minus 1. So what I'm going to do is I'm going to calculate this and store it, right? Because it looks like it's going to be kind of a weird number. So I get, starting in here, 0.05 divided by 4. 0.05 divided by 4 is 0.0125. I'm not going to write that down because I'm just going to add it to 1. And then to the power of 4 divided by 12, and then minus 1, I get 0.0004149425123. Sorry, my calculator showed it in scientific notation, so I actually have more decimal places than you do. But either way, I'm going to store this in 1. Okay. So what I want you to do is try this. Now that you have I2, there's really nothing more to it, right? Notice that I1 and I2 are slightly different because you're going from quarterly to monthly. But I promised to let you go early. So here we go. Do this on your own, and we'll use it for review next day. Try on your own for next day. But you can do it. Okay. Thanks, guys. If you have any questions, let me know. Otherwise, I will see you Thursday.